Hi everyone. Today we'll understand the derivative as a function. Let's first use a limit definition of the derivative to find the derivative of x squared at x equal to 3. And if you don't know what the limit definition of the derivative is, I will add a link in the video description to a video explaining the limit definition of the derivative at a point. For this problem, I will use the limit definition of the derivative that uses h. If you would like to try this exercise on your own first, download these notes using the link in the video description. I get the limit as h goes to 0 of f of 3 plus h minus f of 3 divided by h. Then I plug in the inputs to the formula of the function. I plug in 3 plus h to x squared and 3 to x squared. And I get 3 plus h squared minus 3 squared divided by h. The next step is to square the parentheses, and I get 9 plus 6h plus h squared minus 9 divided by h. The first term and the last term go away. The remaining two terms have h in them, so I will factor it out, and I get h, 6 plus h divided by h. This allows me to divide out h, which leaves me with the limit as h goes to 0 of 6 plus h. Nothing stops me from plugging in h equal to 0 anymore, and I get 6. If I asked you to repeat this exercise, but this time at x equal to 4, could you do it? What about at x equal to 5? I believe that the procedure would be the same. The numbers could be slightly different, but the steps would be the same. Here is the idea. Instead of repeating these computations for different x's over and over again, what about we'll do them once for x equal to x? Let's try. If you would like to try this on your own first, stop the video now. I follow the same steps. I take the limit as h goes to 0 of f of x plus h minus f of x divided by h. Instead of using 3, I'm using x. This gives me the limit as h goes to 0 of x plus h squared minus x squared divided by h. I square the first parentheses, and I get x squared plus 2xh plus h squared minus x squared divided by h. The first term and the last term go away. The remaining two terms in the numerator have h in them, so I will factor it, and I get h, 2x plus h divided by h. This allows me to divide out h, and I get the limit as h goes to 0 of 2x plus h. All I do now is plug in h equal to 0, and I get 2x. What we just found is a shortcut to finding derivatives of the function x squared. You no longer have to go through all these steps anymore. If you want to find the derivative of the function x squared at x equal to 5, you simply plug in 5 to this expression and you get 10. So the derivative of x squared at x equal to 5 is 10. If you want to compute the derivative at 7, you plug in 7 to this expression and you get 14. Can you find such shortcuts for other functions besides x squared? Today we will find two such shortcuts. The shortcut for the function square root of x and the shortcut for the function 1 over x. Before I show you how to find the shortcuts, I have one more comment. Note that this derivative is no longer a number. It is a function. So you can think about derivatives as functions if instead of plugging in the number in the limit definition, you keep that number as x. As a result, you get a function that depends on x. When you're given a function, the derivative function, usually just called the derivative, denoted by f prime, is given by the limit definition of the derivative at a point with the point replaced by x. Let's now try to find the derivative function of the function square root of x. I start by using the limit definition. The limit, as h goes to 0, of f of x plus h minus f of x divided by h. This gives me the limit, as h goes to 0, plug in the inputs into the formula, so I get square root of x plus h minus square root of x divided by h. Note that I can't simply plug in h equal to 0, because then I get 0 divided by 0. I use a method called multiplication by the conjugate. I multiply this by x plus h, square root of x plus h, plus square root of x, both in the numerator and in the denominator. If you don't know this technique, the link in the video description leads you to a video explaining this technique called multiplication by the conjugate. This gives me the limit as h goes to 0. When I multiply the numerators, I will get x plus h minus x. When I multiply the denominators, I will get h square root of x plus h plus square root of x. In the numerator, x and negative x go away. So all I have left in the numerator is h. That h can divide out with the h in the denominator, leaving me with the limit, as h goes to 0, of 1 divided by square root of x plus h plus square root of x. Now I plug in h equal to 0, and I get 1 divided by square root of x plus square root of x, which gives me 1 over 2 square root of x. The derivative of the function square root of x is another function, 1 over 2 square root of x. Let's do the same thing for the function 1 over x. If you would like to try it on your own, stop the video now. I start with the limit definition. I write the limit, as h goes to 0, of f of x plus h minus f of x divided by h. Now I use the formula. I plug in x plus h to the formula and x to the formula, and I get the limit, as h goes to 0, of 1 over x plus h minus 1 over x divided by h. Again, I can't simply plug in 0, because then I get 0 divided by 0. To compute this limit, I find the common denominator in the two fractions in the numerator. I will multiply the first fraction, top and bottom, by x, and I will multiply the second fraction, top and bottom, by x plus h. And I will get, in the first fraction, in the numerator, x, in the denominator x, x plus h. In the second fraction, I will get x plus h in the numerator and x plus h in the denominator. Everything gets divided by h. Because the fractions at the top have the same denominator, I can add their numerators, and I will get x minus h. This minus applies to both terms. This means x and negative x go away, so all I have left in the numerator is negative h. Now, to deal with this triple fraction, I need to recall that dividing by h is the same thing as multiplying by 1 over h. And I get the limit, as h goes to 0, of negative h, x plus h, multiplied by 1 over h. Instead of dividing by h, I multiply by the reciprocal. This allows me to divide out h's, and I am left with the limit, as h goes to 0, of negative 1 of x plus h. I can now plug in h equal to 0, which will give me negative 1 over x squared. We found 3 shortcuts for 3 functions. Let's write them down. For x squared, the shortcut is 2x. For square root of x, the derivative was 1 over 2 square root of x. And for 1 over x, the derivative was 1 over x squared with a minus in front, negative 1 over x squared. Knowing these shortcuts simplifies finding derivatives. Let's see. If you would like to try the next problem on your own first, again, this is a good time to stop the video. To find the derivative of x squared, at x equal to negative 3. I can now use the shortcut instead of using the limit definition. I know that the derivative is 2x. So if I want to find the derivative at negative 3, I simply plug in negative 3. I get 2 times negative 3, which is negative 6. The derivative is negative 6. For the derivative of square root of x at x equal to 9, I follow the same procedure. I know that the derivative is 1 over 2 square root of x. So I simply plug in 9 to this shortcut, and I get 1 over 2 square root of 9, which is 1 over 2 times 3, which is 1 over 6. I know that the derivative of the function 1 over x is the derivative function negative 1 over x squared. When I plug in 1 to this expression, I get negative 1.